Hello students and welcome! Today we're going to talk about two very important concepts in physics, the law of conservation of energy and power. Now these are not just some difficult terms from your textbook, these are fundamental rules that explain everything around us, from a simple ball falling to the ground to how electricity works in our homes. So let's begin.
So this is our plan for today. First, we'll have a quick recap of energy. Then we will understand the law of conservation, which is very important. We will see how this law works in a real example. After that, we will learn about power, solve a few numerical problems, and finally, we will summarize the key differences.
All right, before we go forward, let's remember what we already know about mechanical energy. We have studied two main forms, haven't we? The first is potential energy. This is the energy that is stored in an object because of its position. For example, a book kept on a high shelf has potential energy. And the second is kinetic energy. This is the energy of motion. So when that book falls, it has kinetic energy.
Now I have a question for you all. Think about this. Imagine a fast-moving cricket ball. It has a lot of kinetic energy, right? And then it hits the wickets and suddenly stops. So my question is, where did its energy go? Did it just vanish? Let's try to find the answer.
Well, the answer to that question is found in one of the most important rules of science, and that is the law of conservation of energy. This single law is the key to understanding what happens to energy in any process. The law itself is actually quite simple. It says that the total amount of energy in a system that is closed or isolated always stays the same. It is constant. So energy is never really lost, it just changes its form. In our cricket ball example, the kinetic energy did not disappear. It was converted into sound energy, you hear the sound of the wickets breaking, and some heat energy from the impact. Please pay close attention to this statement. This is the heart of the law. Energy can only be converted from one form to another. It can neither be created nor can it be destroyed. The total energy in our universe has always been and will always be the same.
Okay, so that's the theory. But let's see how this law works in a practical, everyday example. We will look at a simple object that is falling freely only under the influence of gravity. Let's imagine we are holding a ball at a certain height. At this highest point, it's not moving, so its kinetic energy is zero. All of its energy is potential energy. Now, we release the ball. As it starts to fall, its speed increases. This means its stored potential energy is being converted into kinetic energy. And just before it touches the ground, it is moving at its fastest speed. So, at that point, its kinetic energy is maximum, and its potential energy is almost zero. Now, this sum of potential energy and kinetic energy at any point is called the total mechanical energy of the object. And here is the important part. As per the law of conservation, this total mechanical energy remains constant throughout the fall. The energy just changes from potential to kinetic, but the total sum is always the same. Let's look at the numbers to really understand this. This table shows the energy of a 20-kilogram object dropped from a height of 4 meters. You can see, at the top, at 4 meters, the potential energy is 800 joules and kinetic energy is 0. The total is 800. Now, as it falls, look at what happens. The potential energy decreases, but the kinetic energy increases. And the most important thing to see is that last column. The total energy at every point is a constant 800 joules. This proves the law. Okay, so we understand that energy is the ability to do work. But this brings up another question. Does it matter how fast we do the work? The answer is yes, it matters a lot. And this brings us to our next topic, which is power. Power is all about the speed at which work is done. Let me give you a very simple example. Imagine two people have to climb a flight of stairs. They both have the same weight, and they climb to the same height. This means they both do the exact same amount of work. But one person runs up the stairs quickly, and the other person walks up slowly. The person who ran did the work in less time. So, in physics, we say that the person who ran is more powerful. So, this is the formal definition of power. Power is the rate of doing work. That word, rate, is very important. Whenever you see the word power in a physics problem, you must immediately think about time. Power tells us how much work is done in a certain amount of time. And this brings us to a very simple formula. Power, which we write as P, is equal to work done, W, divided by the time taken, T. So the formula is P equals W divided by T. The SI unit for power is the watt, named after James Watt. Now, what does 1 watt mean?
It simply means that 1 joule of work is being done every second. You see this unit written on many appliances in your house. For example, a bulb might be a 100-watt bulb. For bigger appliances, like an air conditioner, we use a bigger unit called the kilowatt. 1 kilowatt is simply 1,000 watts.
All right, we have understood the theory, but the best way to really understand a concept in physics is by solving some problems. So let's solve a numerical together, step by step. Here is our first problem from the textbook. There is a girl, let's call her Girl A. Her weight is 400 newtons. She climbs up a rope to a height of 8 meters, and she takes 20 seconds to do this. We have to calculate her power. Now, what is the first step we always follow when solving a numerical? We write down all the information that is given to us. So, we are given her weight, which is the force, as 400 newtons. The height, or distance, is 8 meters, and the time taken is 20 seconds. Okay, let's calculate. First, we need to find the work done. The formula for work is force multiplied by displacement. So, work is 400 newtons times 8 meters, which comes to 3,200 joules. Now we can find the power. The formula for power is work divided by time. So, power is 3,200 joules divided by 20 seconds, and our final answer is 160 watts. Now let's look at the second part of the problem. There is another girl, Girl B. Her weight is also 400 newtons, and she climbs the same height of 8 meters. So she does the same amount of work. But notice she is slower. She takes 50 seconds. So what is her power? The work done is exactly the same, 3,200 joules. But the time taken is different. It's 50 seconds. So for Girl B, the power will be 3,200 joules divided by 50 seconds. This gives us 64 watts. So you see, even though both girls did the same work, Girl A was more powerful because she did it in less time.
Very good. So let's now quickly summarize everything we have learned today. It's very important to remember the difference between energy and power, as students often get confused between them.
So, to be very clear, energy is the capacity or the ability to do work. Its unit is joules. Think of it as the total amount of petrol in a car's tank. Power, on the other hand, is the rate at which that work is done. Its unit is watts. So power is not about how much petrol you have, but how fast your engine is using it. The main difference is always time. And finally, I'll leave you with a question to think about. We learned that energy cannot be created or destroyed. So think about the electricity in your home. It starts as chemical energy in coal at a power plant. How does that energy change forms, step by step, to finally become the light from your bulb? Think about all the energy transformations. Thank you.